Okay, question number 13 of the worksheet on forces on threaded rings. Okay, it says that a small ring R is attached to one end of a light inextensible string of length 70 centimeters. A fixed rough vertical wire passes through the ring. It's rough, that means there needs to be friction. Okay. The other end of the string is attached to point A on the wire vertically above R. A horizontal force of 5.6 Newton is applied to the point J on the string 30 centimeters from A and 40 centimeters from R. The system is in equilibrium. That means up force equals down forces, right forces equals to left forces, which with each of parts JR, AJ and JR of the string taut and the angle AJR equals theta. Find the tension in part AJ of the string and find the tension in part JR of the string. Okay, so we'll have to look at J and outwards write T1 and here outwards write T2. Okay. I need a theta in this question so that I can find cos theta and tan theta, sorry, sine theta to resolve the tensions. Okay, I can find this angle, or better, I can find sine theta and cos theta of this angle. Okay, so we have 30 here, 50 here, 40 here. We can use Pythagoras and get this length as well. Going to do square root 30 square plus 40 square. This will give us 50. So this is 50. That means sine theta is going to be 40 over 50, which is 4 over 5. And cos theta is going to be 30 over 50, which is 3 by 5. Okay. Now let's resolve the forces at T. So at J, sorry, we have T1 here and we have a theta here. This would be the left component. This would be the up component. Okay, so we have yeah, T1 towards one component of T1 in this direction, one component of T1 in this direction. Okay, this would be the, oops, what happened here? Just a second. So there was a horizontal component, a vertical component. Okay, since the horizontal component is opposite to theta, this one is going to be T1 sine theta. And since this upward component is the adjacent component, it's going to be the cos component, T1 cos theta. And instead of writing the upward or making the upward component here, I can also make it here. This is J. Okay, so now this would be T1 sine theta. And this one would be T1 cos theta. Okay. Similarly, let's take a look at T2. Okay. For T2, if I make a triangle like this, then I do not have this theta in this triangle, or do I? Let's see, I might have it somewhere. Okay, so this is 90, and where would this theta go? Trying to establish where will this theta go in this triangle. Okay, that is this angle here is going to be 180 minus 90 minus theta, meaning it would be 90 minus theta. So this is 90 minus theta, which means this angle here is going to be theta. How? I'm going to do 180 minus 90 minus again 90 minus theta. Open the brackets, we get 180 minus 90 minus 90 plus theta, which these gets cancelled and this is theta. So this is also the same angle theta, the black one. Okay, let me clear this and mark theta over there. Yes, so this is theta as well. Now, when we resolve T2, it will have a horizontal component is this direction and a vertical component in this direction, but I'm going to plot it here instead. Okay. Now, the one opposite to the angle theta is going to be the downward component. This one is going to be T2 sine theta, and the other one is the adjacent component, so T2 cos theta. Okay. Now let's equate the right forces, the left forces, and the up forces and the down forces. So if I equate the left forces, there are two here. And with the right forces, I'll write 5.6 is equals to T1 sine theta plus T2 cos theta. So 5.6 is equals to T1 times 4 by 5 plus T2 times 3 by 5. Okay. Now I'm going to equate the up force with the down force. So we have T1 cos theta upwards is equals to T2 sine theta downwards. There's no weight on J, so there's no other third component in the vertical plane. Okay. This would be T1 3 by 5 is equals to T2 4 by 5. I'm going to cancel these, so I get 3T1 is equals to 4T2. Now I can solve this and this simultaneously and get T1 and then T2. Okay, let me just see if all is going well. Okay, so I will write T1 equals 4 over 3T2. So 5.6 is equals to, instead of T1, I'm writing 4 by 3 T2 times 4 by 5 plus 3 by 5 T2. So I get 5.6 is equals to 16 over 15 T2 plus 3 by 5 T2. Take T2 common and then divide the sum you get on the right hand side with 5.6. 5.6 is equals to 16 by 15 plus 3 by 5 is 5 by 3. T2, so T2 is equals to 5.6 into 3 divided by 5, which gives us 3.36. Okay. Now I would like to find T1. For that, I can use this. T1 equals 4 over 3 times 3.36. So answer times 4 by 3 in the calculator, which gives 4.48. Okay, that's done. Now, T1 is found and T2 is found. Part 1 is done. Part 2 says the ring R has a mass of 0.2 kg and is in limiting equilibrium on the point of moving up the wire. Okay. Now, let's mark that weight on R. There's going to be a downward force of mg newtons, which is going to be, what was the mass again? 0.2. So this is going to be 2 Newton force. Okay. Now the object is about to move up the plane. That means friction is also down the plane. So we have F or mu R down the plane. Okay. Now, since the pull on the rod is in this direction because of J and this 5.6 Newton force, the contact will take place here and the normal contact will be in this direction. So we have normal contact force R horizontally towards the right. Please don't get confused by both the R's. This R is because of the ring and this R is what we call the normal contact force. Okay. Now there would be two more forces acting on R. That would be the components of tension, this tension. Now from R's perspective, T2 is going to be outwards. T2 is the tension in this string, and we have already found its value. It found its value earlier. Okay. So now we're going to resolve it. There's going to be a force in this direction, and there's going to be a component in this direction. Let's mark it. Okay, here's T2, and here was theta, and there's going to be an upward component and a right component. So an upward component and a right component. Upward component is going to be the sine component because it's opposite to the theta. So T2 sine theta, and this one will be the cos component, T2 cos theta. So let's write that down. T2 cos theta, and this is T2 sine theta. Okay. Now find the coefficient of friction. For that, we will be again equating the up forces with the down forces. We have an up force T2 sine theta, and that is the only up force we have, is equals to their two downward forces, 2 plus mu r. Coefficient of friction is already given. Achani, show that the coefficient of friction is that. So we have to find the value of mu, and we know what is T2. T2 is 3.36. We know what is sine theta. Sine theta had come out to be 4 by 5 minus 2 is equals to mu, and R would be, for R we equate these forces. We have R equals T2 cos theta. So R equals 3.36 times 3 by 5, which is 2.016. Okay. Now, what do we have? Okay, we need to use this R here, 2.016. Now let's find mu by dividing the answer here, 3.36 times 4 by 5 minus 2 upon 2.016. Let's see what do we get. So 3.36 times 4 by 5 minus 2, answer divided by 2.016, which gives me 0.34126. So mu comes out to be 0.34126. Next up is a particle of mass m kg is attached to R, and R is now in limiting equilibrium on the point of moving down the wire. Given that the coefficient of friction is unchanged, find the value of M. Okay, let me make space for this here. Okay, so let's look at R again. R has a weight in this direction which stays unchanged too, but now R is moving downwards, meaning now the friction not moving downwards, but it is about to move downwards. So then the friction would go upwards. And also because of this T2 here, we still have an upward force of T2 sine 30 theta as done in the last part. This one, T2 sine theta. And similarly, we have T2 cos theta in this direction. And R is the normal contact force is still in this direction. The only thing that has changed is the direction of the friction, which is now upwards. Earlier it was downwards. Okay. And also I've missed this. A particle of mass m kg is attached to the ring. So now the downward weight is not just going to be 2. It's going to be, the new mass is going to be 0.2. Where was the mass earlier? Okay, here was the mass. So this is going to be 0.2 plus m times 10. So mg is now going to be this. Okay, a particle of mass m kg is attached to R, and R is now in limiting equilibrium on the point of sliding down the wire. So that means friction is backwards or upwards. Given that the coefficient of friction is unchanged, find the value of m. Okay. So again, we're going to equate all the forces. Okay. So it's going to be uh, up forces T2 sine theta plus R, no, plus mu R is equals to 0.2 plus m times 10. Okay. T2 we had found earlier, and I've seemed to have cleared it. What was the value of T2 we had found? 3.36 times sine theta. Sine theta was 4 by 5 plus mu was 0.34149. Okay, times R is going to be, R is left force, so right force is T2 cos theta. Let's use that. T2 is 3.36, cos theta is 3 by 5, is equals to 0.2 plus m times 10. Okay, the only unknown here is m. Let's find it out. So we have 3.36 times 4 by 5 plus 0.341 times 3.36 times 3 by 5. That is so many numbers. Okay, I'm getting 3.375 is equals to 0.2 plus m times 10. So I'm going to divide the answer with 10, subtract 0.2 from it, and I get 0.3175. So m is coming out to be 0.13754, rounded to 3 significant figures, 0.138 kgs.